So let's start the meeting. So yeah, good morning, good afternoon, good evening, everybody. So thank you very much for gathering to the annual briefing of CaMa-Flood progress report. So yeah, this is our first event we've organized. And anyway, yeah, thank you for very much for joining this event and contributing to CaMa-Flood researches or being interested in our activity. So yeah, this meeting is named our CaMa-Flood annual briefing. And the primary purpose of this meeting is to highlight the research using CaMa-Flood published in 2022 to 2024, and to make these researches visible among the CaMa-Flood community and beyond. And yeah, actually we had a on-site meeting in last year, July in Tokyo. But yeah, this is more for discussions, but for online annual briefing, we'd like to focus more on the published papers in recent years. And because this briefing event is first attempt this time, so we also highlight several historical milestone papers before 2022. So this is what happens tonight. And for presenters, thank you very much for cooperating to make the annual progress report. And now the PDF version of the progress report 2024 is available online. So you can download from this QR code, or the PDF is put on this meeting webpage. So please visit there and yeah, get the PDF version. And this PDF report contains a link to the all papers. So if you are interested in talks today, please check the original published papers. And this and also this online meeting is recorded to make a video report. And I'm thinking about uploading it to CaMa-Flood webpage later, so that you can advertise your work to many people. So this is how this meeting works. And so this is a note. So for presenters, please be precise on your talk time. And we appreciate if you provide a brief summary and highlight. And then audience can check details in the published paper. So this is how the meeting works. And the participant, I'm sorry, maybe we don't have adequate time for question and answer this time. So I appreciate if you can ask questions on, not on Slack, on chat. So please ask questions on chat. So thank you for your cooperation. And today's program is like this one. So first session is the status of the CaMa-Flood core developments. And the second session is review on the achievement reports. And session 2A is a highlight on the historical milestone papers, and we have 4 talks. And session 2B, we focus on the recent CaMa-Flood development papers, and we have 6 talks in this section. And session 2C, we review the CaMa-Flood application papers, and we have 7 talks. And at the end, we have a session 2D. So that's focusing on new data or new tools for CaMa-Flood. So we have in total about 20 presentations today. Okay, so yeah, let's enjoy today's meeting. And I'd like to move to the session 1. And session 1 is about the review of the CaMa-Flood recent core development. And I myself will present about the major update of CaMa-Flood in recent 3 years. And Xudong will explain the CaMa-Flood accuracy evaluation status. So first, let me present. Okay, so yeah, today I'd like to explain the major update of CaMa-Flood in recent years. And yeah, first I'd like to review. So we released CaMa-Flood version 4 in March 2021. So this is our major version update of CaMa-Flood, which contains first upgrade of the baseline topography data using merit DMs and merit hydro. So previous CaMa-Flood version 3, it's based on SRTM and hydro sheds, but we've updated the baseline topography data to merit hydro. And by updating the topography, we clearly observe the improvement of the simulated flood hydrodynamics. And so this is a major update we made in version 4. At the same time, this is for expert, but we refactored the CaMa-Flood source code structure a lot to allow more flexibility for users. So it's a bit technical, but what happened is now we have the CaMa-Flood itself is highly modularized. So yeah, have the CaMa-Flood source code is divided into several parts, and how the many can be used as a library. And because of that, we can do very flexible use of CaMa-Flood. Like, yeah, the package distributed is a CaMa-Flood standalone driver, but by slightly modifying the code, like adding the additional code for coupling, we can easily couple CaMa-Flood with other models, like atmospheric models or land surface models. So this is the, how to say, one of the major advancement in CaMa-Flood version 4. And yeah, code is refactored following the ECMWF standard. And now coupling of CaMa-Flood with other Earth system model becomes very easy. So this is what I've done in version 4. And today I'd like to introduce what happens after the release of version 4.0. So the first update is release of version 4.1 in January 2023. And this update is primarily for the improvement of the computational efficiency. So first, I implemented the single precision mode, which use single precision variables instead of the double precision variables, except for a few variables very important for mass balance. And actually what we've achieved is we succeeded to double the simulation speed without accuracy degradation. So the simulation speed is twice as fast as the previous versions. And in addition, we implemented the MPI and OpenMP hybrid parallelization. And now the CaMa-Flood calculation can be distributed to 16 different MPI nodes. Or if we neglect several minor bifurcation channels, we can distribute CaMa-Flood calculations onto up to 30 computers. And this makes the simulation simulation speed very fast compared to the previous versions. And so this is a summary on the simulation speed. So if we use the only OpenMP on 20 cores, 1 year simulation for 50 minutes resolution took about 8 minutes. But how to say, using MPI, it can be much faster. And we found out the simulation speed is faster when using MPI, OpenMP, hybrid parallelization, rather than simply using only MPI, only OpenMP. And because we can distribute simulations on more processors, how to say, now I can say the global super high resolution simulation using CaMa-Flood becomes possible if we have access to our high performance computer cluster. So this is the status of version 4.1. And in last year, April, we released the latest version 4.2. And this version's major update is on the reservoir operations. So yeah, we improved the reservoir operation schemes. And how to say, now we treat reservoir operation as a kind of a default option. So this can be safely activated in your simulations. And what we propose is actually a more stable reservoir operation schemes by solving several issues in previous reservoir operation. And yeah, we carefully examined the equations used for the reservoir operation schemes. And yeah, we found a way to secure the flood control capacity during non-flood period. And also, this is very important. So we implemented smooth discharge functions to avoid instability. So yeah, detail will be explained in the description paper, but in previous models, actually oscillation of the reservoir outflow happens But by using the new scheme with smooth discharge functions, we succeeded to stabilize the reservoir operations activity. Anyway, the stability is largely improved, and now we have a confidence to use this new reservoir operation scheme as a default. So this is a major update in version 4.2. And last but not least, we have another major update on CaMa-Flood recently. So in version 4.2, we've enhanced documentations. So manual is updated. And in addition to the main manual, we wrote lots of supplementary note and sub-manuals for the advanced schemes. So these are saved in the doc directory in CaMa-Flood. So if you have some troubles on using CaMa-Flood, or if you want to know the details of the scheme, yeah, now we have many documentations. So please check these documentations. So yeah, anyway, some are minor, but I think CaMa-Flood usability is increased a lot. So yeah, so this is report from myself. So I hope this one is very useful. Okay, so this is a report from myself, and I'd like to move to the second summary on G2. So Xudong, could you please present your achievement?
Okay, can you see my slide?
Oh, yes, please start.
Okay, hello everyone. So very happy to gathering here and to see many faces. So to share this big moment, and I'm so proud that I was working in the lab for last 4 or 5 years, and now we have some new result. And this is a paper which is published this morning. So I'm very happy to share the happy news with everyone. And this is a benchmarking framework for the global river models. And we have been working on this for many years. The background for this system is that we know that there are many increasing demands of the model comparison, including the model validation, model development, and the inter-comparison with other models. Yamazaki Sensei just shared what we have done for the CaMa-Flood development for the last few years. So we know that there are super high demand for the comparison. And also the calibration of the CaMa-Flood is a high need in the future, in the coming years. And then in the system, we also have to know there is some limitation because up to now, the river discharge is the most important variable which we rely on the calibration. But we know that discharge observation is limited in the space and time. In the large area in Asia, in the Africa, we don't have enough or sufficient river discharge observations for that. And on the other hand, river discharge is only one hydrology variable, but we know that the hydrodynamics variables, including the water surface elevation and water surface area, is also important, super important for the flood, especially for the flood. So we integrate the hydroweb, which stands for the water surface elevation, and some other satellite variables, including the Landsat GIMS, which represent the water surface area in the system. And in this simple diagram, we know that there are only a few areas with river discharge observation and water surface elevation. They have some overlaps, but for the water surface area, it has large area covering the entire land. So we know that the variables for the water surface elevation and area are also important. And the purpose for the benchmarking system is we know that what is the benchmarking, and explanation is that to measure the quality of something by comparing it with something else of an acceptable standard, and what we wanted to do with the benchmark is to provide at least a standard, and then based on this standard, we can know easily how the development of CaMa-Flood is achieving by comparing the reference. And in the system, we have a few steps. First of all, the simulation is important because we know the purpose is to compare our improvement with the reference. And the system has the observations, including discharge, the water surface elevation, and the water area. And we have to do some pre-processing, including the allocation for the river discharge, allocation for the water surface elevation, and also upscaling or downscaling of the GIMS water surface area data. And based on the simulations and observation, we will do the reformatting or matching the simulation and observation in the same location or same area. And then the system goes to the model assessment. Assessment including to evaluate the performance metrics. And then also we have built up some metrics for the model comparison. And the last part is visualization, which allows us to easily see how the model is changed. And for the allocation, there are a few steps which is based on our previous works. So the first allocation of the river discharge, we can see the cause in the online version, and also for the allocation of the visual station, we can see the publication by Menaka, and the links are also included in the PDF version. And now this is for the water surface area. We build up the flow plan mask so that we can compare our simulation within a reasonable area. And for the metrics, we have built up many metrics, including the p-bias, or which stands for the status of the hydrodynamics, and also some evaluation metrics for the entire time series. And this is only a part, but in the code, we also include other metrics which are not shown in the paper. And in addition to the evaluation metrics, the comparison metrics, we have built up 3 metrics. The basic is the relative score, and also the change in the ratio, and also we have the overall percentage change, which is our novel method in the paper. And for the visualization, we have a very simple heat map. And in this heat map, we can compare the different, this is the model evaluation, different setting of the models, and this is the matrix. And we can see from the color how the model is changed from the reference one. And for some cases, in the paper, we evaluated the changes in the runoff generation, including Earth to observe ECMWF, ERA5, and weak bias corrected. And then we can see from the result that the weak bias corrected, which shows the blue color here, it means this model simulation is better than the others, including the reference one, Earth to observe ECMWF, and the ERA5. And we also can see from the benchmarking system how the changes is distributed in the global area. And including the river discharge, we also have the water surface elevation comparison and the water surface area. And from this heat map, we can see for the two variables, surface elevation and the surface area, the model is still has large space to improve compared to the river discharge. And from this year, we are planning to regularly update the accuracy report of CaMa-Flood and its updated versions, but we also need some help from you that if you can join us to contribute to the benchmarking. Also, if you can provide some versions for us to do the benchmark, and we are happy to see any like demands from you, and we can apply this system to your work. Thank you.
Okay. Oh, thank you very much, Xudong. Congratulations on the publication of the benchmark papers. And I think from next year, we can continuously observe how CaMa-Flood accuracy is improved from previous year. So I'm looking forward to seeing that. Okay, so let's move to the second session. And it's on the highlight of the milestone papers. And I invite 4 presenters who made, a big advancement of CaMa-Flood research. So first, we'd like to start from Professor Yukiko Hirabayashi, and then Professor Fang Zhao, and then Wei Ping Wang and Julian Boulange with our talk. So Yukiko, could you please share your screen and start presentation?
Thank you very much, Dai. I'm Yukiko Hirabayashi from Shibata Institute of Technology. Because I'm one of the oldest or the first user of CaMa-Flood, so Dai kindly invited me to talk a bit about all the publications. Here's the framework of flood damage calculation using CaMa-Flood. So we first calculated flood exposure, loss, and damage in the past using the reanalysis experiment runoff obtained from reanalysis data. So the annual maximum water storage is calculated at 15 minutes, and then it was downscaled using high resolution elevation data like Meritodem to the about 1 kilometer or 30 seconds. So, and then we created a lookup table of this, the 15 minutes return period of annual maximum water storage, and this the exposure or damage. The lookup table was then applied to past and future climate experiment. Even though the climate simulation has a coarser resolution like 1 degree, the lookup table provides exposure or loss and damage at a finer resolution, like the 1 kilometer with less bias. So this framework relies on the global flood calculation CaMa-Flood, which enable us to calculate inundation extent based on elevation data at finer spatial resolution. So this paper published in 2013, very old paper, but it presented the first result using this framework. So here is the first estimation of multimodal flood change on global scale. So we showed, for example, in Asia, Africa, and South America, flood frequencies are predicted to increase with high consistency among climate models. Using the lookup method, we also calculated exposure, the number of people affected by flooding. Here you can see that exposure is projected to increase, especially after 2015, depend on emission scenario. You can also see that flood exposure increase in associated with temperature rise. So the paper was cited in the IPCC 5th assessment report like this. This paper published in 2021 in Scientific Reports is almost the same as the paper in 2013, but with the latest CIMIC-6 experiment. So it showed that both frequency change and model consistency was very similar between CIMIC-5 and CIMIC-6. And with minor difference in some places where the low consistency region. And that was cited in the IPCC 6th assessment report. So we did this work because for the IPCC report. So this paper that published in nature climate change in 2021 is we extend the exposure and damage calculation framework of CaMa by adding adaptation scenario and cost benefit assessments. So we first calculated a probable flood protection level under specific adaptation scenario strategies using the cost benefit assessment. We then calculated residual flood damage that exceeds the protection level. The results showed that adaptation limits occur in most regions. Because the residual flood damage can be mitigated, it is not shown in this slide, under intensive adaptation strategy, we can conclude that international financial support can help reduce damage. We also found that early adaptation decisions are important due to a large proportion of damage that occurs while flood protection facilities are being built. And this is the last paper that published in Scientific Reports in 2022. So we utilized that framework for event attribution experiment of past flooding that occurred between 1951 to 2010. We found that human-induced climate change affected probability of occurrence for about 38%. The 20 events occurred during that period. And that is mostly in Asia and Africa and northern South America. So interestingly, all recent floods after 2000 showed an increase in probability of occurrence due to past human-induced climate change. So I'm sorry for so many papers that I quickly explain, but here's the summary. So yeah, because the time is limited, I will stop. So thank you very much for your kind attention.
Yeah, oh, thank you very much, Yukiko, for introducing actually 4 papers in 5 minutes. It's amazing. And I really appreciate using CaMa-Flood so heavily in your kind of entire career. So yeah, thank you very much. So I'd like to move to our next presenter. So next one is by Dr. Fang Zhao. Could you please share your screen?
Sorry, I'm not quite sure. Is the screen showing?
Oh, yes, it's showing. So, okay. So
Okay, good. Okay. Thanks, Dai, for the invitation. It's been an honor to present here, and it's also like one of the earlier papers for the CaMa-Flood kind of sort of performance benchmarks, because I was in the ECMIP coordination team, and we want to use the CaMa-Flood for this large-scale analysis. And the first question is that because CaMa-Flood does not have those human factors like reservoirs and human water use, then how good is the simulated discharge by CaMa-Flood? So in this study, what we do is we have over 9 different global hydrological models inside the ECMIP project, which we basically coordinate a number of modeling teams to do hydrological simulations and based on like climate data, bias corrected data. And these models themselves both have simulated the runoff and they have a discharge, but it's according to their own routing scheme. In simulating discharge, some of them also have like human impact simulations. And then, but this runoff basically gridded runoff is what we use also to be able to drive the CaMa-Flood simulation to get these simulated discharge patterns, very similar to the hydrological models discharge patterns, such that we can do a pairwise comparison to see whether CaMa-Flood improves or deteriorates compared to the original model's discharge simulation using a global network of over 1,000 stations with daily data. And because these are not like large-scale models, so we also have a criteria to limited comparison to only large basins and do the comparison for these basin averages performance for each of the basin. We do that instead of comparing at the outlet because for flood implications, like it's important to simulate well, not just at the outlet, but everywhere in the river basin. So in this way, by using the average performance of the stations, we accounted for in general whether CaMa-Flood improves or improves the performance of discharge simulation, especially for the peak discharge. So the main effect of this CaMa-Flood simulation is that it generally tends to delay the flood maximum peak discharges occurrence date. And below is the magnitude. The red color shows reduced magnitude. And you can see that there are like CaMa-Flood are in the red line, which and the hydrological model is the blue line. So it generally shows a delay, and whether it improves, it depends on how well the original model is. But that's like the general effect we can expect from the CaMa-Flood simulation. And when we check the performance, especially when you look at the peak discharge, so basically this lower panel is the maximum discharge bias with for the whole period, whereas the right panel is like multi-year maximum, multi-year mean of annual maximum bias. And green color shows at least 5% improved performance compared to the hydrological model's original simulation. And you can see that while the Nash efficiency is not is relatively similar, the big improvement can be seen in this peak discharge simulation. So why is that? This first suggests that the routing scheme really matters, that CaMa-Flood's routing scheme actually in general shows an improved this peak discharge simulation and compared to the hydrological models. This is because of the explicit consideration of the floodplain storage, which serves as a buffer to reduce the peak and delay the peak discharge time. Without the buffer, the hydrological models tend to simulate a too early peak and too large peak. And this figure shows for that the strength of this effect. So that's my talk today. Thank you.
Okay, oh, thank you very much, Fang. Oh, it's very nice to hear this presentation again. So yeah, it was, I think, huge milestone to show that the river routine is very important, and maybe physics-based representation works very well. Okay, oh, thank you very much. So I'd like to move to the next presenter. I heard Wei Bin might be able to present, but he might be needed to do video talk. So, Wei Bin, are you here? Maybe he is not, so I will share his talk by video. So yeah, let me start. Oh, wait a minute.
Hello, everyone. My name is Ping. I come from Beijing Normal University. Thank you very much for the invitation from the Professor Dai, and thanks everyone for having me. CaMa-Flood has been of great help to my research. I'm honored to be able to have the chance to share some of my work with you. So, not of my work is motivated by the very busy transportation system that you can use it every day. So, what is transportation? Right here, I'm showing the different models of transportation and the facility. They all belong to transportation, but they cannot fully represent transportation. The primary goal of transportation is to facilitate the movement of humans, animals, and goods from one location to another. This essential functions is achieved through the integration of the three key components: transportation infrastructure, workers, and operations. Floods have a highly destructive impact on transportation system worldwide. So I will present kind of one chunk of my work today. So I'm going to start with a motivate questions of how to measure the impact of floods on transportation infrastructure. Here we explore the floods to road networks of China and the United States. We have many reasons, such as economies. Here we use some methods in complex networks to construct a model to analyze the impact of floods. First, we abstract intersection as nodes and road segments between the section as edges. So I can have a network to represent the road systems. These studies define the disaster impact cause failures and divide them into three groups. Therefore, after we have the model, we are ready to verify the model with real data. We use disaster node data from the Hurricane Harvey event to verify our model. In the existing series of complex network, there are also certain patterns of the disruption. The left figure shows random and localized attacks on road networks. These types of the disruption are considered to be similar to the pattern observed in the nature disaster. If we find that the floods are similar to these two types of the attacks, we can directly apply the hydrological results from these two types of attacks in our research. To explore the characteristics of floods, we compare their disruption effects with those of random and localized disruptions. For the flood simulation, we use the CaMa-Flood model, progressively increasing the surface runoff intensity to generate destructive floods, eventually inundating the entire road network. We find that across the various metrics, the impact of floods varied between those of the random attacks and the localized attacks. Here we aim to examine the spatial distribution characteristic of failures caused by the floods. We found that both floods and localized attacks exhibit the spatial clustering. In terms of the source of the disruption effect, floods cause direct failures, while random disruption lead to indirect failures. In complex networks, both random and localized attacks have been thoroughly analyzed and solved using methods that are universal and computationally efficient, as mentioned before. However, floods exhibit distinct characteristics that sets them apart from these two types of the disruption. Therefore, we have extend the information progression series of complex network to develop an analytical method for assessing the impact of flood disruptions on systems. This method is finally we drive the equations like that. We have a series of studies on the impact of floods on transportation. When considering the impact of transportation infrastructure, we explore complex network series. Workers are introduced into systems. We utilize engine-based modeling, and when operations are taken into account, we applied multiplex network analysis. Due to time constraints, I will not delve into the details today. I also have several other research interests that I hope to discuss and collaborate with all of you. And I will close there. Thank you once again for the opportunity to share my research with you. I have truly enjoyed the exchange of ideas and look forward to seeing even greater advancements in the development of CaMa-Flood models.
Okay, thank you very much, Wei Ping. So I'd like to move to next presentation now. So next one is by Julian. Could you please share your screen?
Yes. Can you hear me?
Oh, yes, it's working.
Okay, perfect. Just give me a second. And how is the slide looking? Is it good?
Yeah, it looks okay. So please start.
Okay, so let me go ahead. So thank you, Yamazaki-sensei, for the opportunity to present this work. So I'm Julien Boulanger. I'm now affiliated with the Tokyo University of Agriculture and Technology. But when this work was conducted a few years ago, I was working together with the second author, Dr. Anasaki. So let me give you a very brief introduction and context about this study. So as shown by the first study in this session, global warming is anticipated to increase flood risk due to change in distribution, variability, and intensity of precipitation. And while estimate of population exposed to river flooding vary widely across a study, it is often reported that between a 4 and 20-fold increase by the end of the 21st century is predicted. Meanwhile, 2.8 million dams have been constructed globally to mitigate flood risk and also provide other benefits. And unfortunately, while most of the biggest rivers are regulated by dam, these regulations are not being physically integrated into global flood impact. So to what extent do they alter future flooding, and the exposure of population to flood in response to climate change is unknown. Another way to frame this study is, so you saw this figure during Hirabayashi-sensei presentation. So in her calculation, this future flood return period were calculated without accounting for dam. So how would this figure look if we consider dam? Is another way of framing this research. So to conduct this analysis, we use two models. So one of them is, of course, CaMa-Flood. And when I did this research, it was still CaMa-Flood version 3. And in this version, dam are not represented And obviously, it can, however, simulate a flood stage or inundation. And the second model we use is the H08 model, which is the global hydrological model. So in this model, it was one of the first global models to actually represent the impact of a dam on hydrology. However, it cannot simulate flood stage. So the idea here is obviously to use the strengths of both models to represent the impact of a dam on floods. And the framework work as such. You first run a simulation with the H08, and which means you have a stream flow output available globally, and then you will run CaMa-Flood. And in this picture, which depict some hypothetical river network, you can see that in this grid cell here, and in this grid cell here, there is a dam located here. So CaMa-Flood was not aware of the presence of the dam. So when we run CaMa-Flood dynamically, for this location only, we will swap the predicted discharge by CaMa-Flood with that of the H08 model. And for the other material method, all dam information come from the Grandi. And for the H08 simulation setting, it was operated under the EasyMIP2 protocol. However, there is one important difference with the EasyMIP2 protocol. Because we are coupling CaMa-Flood and H08, we need to use the same river network. And for this work, we use the river network used in CaMa-Flood. So this is the only aspect that is not consistent with the EasyMIP. In EasyMIP2, at that time, we had access to 4 GCMs, to a future scenario, and we also have access to a historical scenario. The simulations were conducted globally at a daily time step and at a global resolution of 0.5 degree. And here, the idea is we run 2 simulations. So one simulation with dam using the coupling I described in the previous slide, and one simulation without dam, which is the typical CaMa-Flood simulation. For the flood analysis, the calculation of exposure, we follow as much as possible the methodology that was explained at the beginning of this session, so which consists of fitting Gumbel distribution to historical annual maximum discharge, and then assess the frequency of future annual maximum discharge. Let me move to some result. So this figure showed the population exposure to the historical 100-year flood, river flood, as you can see in a million. What is important is in this calculation, we kept population constant at 2010 level, and also this figure is only showing the result downstream of dam. If we look at if we compare our simulation upstream of dam, it is almost identical. It is not strictly speaking identical because CaMa-Flood represents the backflow effect, which may in some case influence the simulation, but it is very minor. And this is a figure that is very similar to that of the first session in this of the first presentation in this session. So we show the frequency of historical 100-year flood in the future, and overall you can see that the visually it looks very similar to the previous finding. But of course, we are now interested in the difference between the simulation without and with dam. So I simply took the differences between the figure obtained with and without dam, and this is this figure here. And you can see that in general, by considering dam, the return, the future return period increases, so flood event become more rare in sense. So it add 100 year to that. But if you look also at the bottom of this figure, you can see that in some few cases, the dam has the opposite effect, and this is most likely due to some limitation of the dam algorithm that is implemented in H08. So to conclude, we found that considering dam in a climate impact study of flood significantly offset the population size exposed to river flood. So dam significantly decrease the risk of future global flood. So for example, they protect an additional 1.4 and 2.3 million people at the end of the 21st century for the 2 RCP that were available in EasyMIP2. And this increase in population that are protected generally come from change in flood occurrence. So, for example, downstream of dams, when we look at the historically 100-year flood, they occur every 107 years in the simulation with dam, but every 79 year in the simulation with no dam. So more often, and this was for RCP26. And if you look at the higher emission scenario, they occur every 59 years with the simulation with dam, but every 46 year on average in the simulation with no dams. So time is limited, so let me finish my presentation here. And if you want to contact me, I have my email address here, and I'm happy to take any further question.
Okay, thank you very much, Julian. So yeah, this attempt on coupling CaMa-Flood and HO8 water resource model is very interesting, and I think we can do much more with this framework.
Thank you.
Okay, thank you very much. So I'd like to move to the next session. So session 2B is on the CaMa-Flood development papers.